Right now, at this moment, you are being passed through by light that is older than the Earth, older than the Sun, older than the Milky Way, light that has been traveling through the universe since before any star existed, since before any galaxy had formed, since the cosmos was a fraction of its current age and a state of matter that has no analog anywhere in the present universe. It is not arriving from any particular direction. It is coming from every direction simultaneously, equally, filling all of space the way water fills a sponge. It is so faint that your eyes cannot detect it. It is so cold that it registers as a temperature only a few degrees above absolute zero. It passes through walls, through the earth, through your body, without leaving a trace you could ever feel. And it is the most important thing we have ever discovered about where we came from. It is called the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang, the oldest light in the observable universe, and the story of how we found it, what it is, what it has told us about the origin and structure and fate of everything that exists, and what it might yet tell us about things so large and so strange that even physicists struggle to hold them in their heads. That story is the deepest and most extraordinary story in all of science. It begins, as so many of the greatest scientific discoveries do, not with a grand experiment designed to answer the ultimate questions, but with two men and a very large antenna, and an infestation of pigeons in New Jersey. Arno Penzias and Robert Wilson were not cosmologists. They were engineers, radio engineers working at Bell Telephone Laboratories in Holmdel, New Jersey in the early 1960s, tasked with developing and improving the technology of radio communication using satellites. Bell Labs was one of the most extraordinary research institutions in the history of science, a private laboratory funded by the profits of the American telephone industry with enough resources and enough intellectual freedom to attract some of the best scientific minds in the world and let them work on problems that might not pay off for years or decades. The transistor was invented at Bell Labs. Information theory was developed at Bell Labs. The laser was refined there. The solar cell. The cellular telephone concept. Bell Labs in the mid-20th century was producing fundamental science at a rate that embarrassed most universities, and Penzias and Wilson were part of that culture. The instrument they were working with was called the Holmdel horn antenna, a 20-foot horn-shaped reflector, originally built to communicate with the Echo balloon satellites, pointed at the sky and sensitive to microwave radiation. By 1963, the satellites it had been built to work with had been superseded by newer technology, and Penzias and Wilson had repurposed it for radio astronomy. They wanted to use it to make careful, precise measurements of radio emission from the Milky Way, a project that required knowing, with great accuracy, exactly how much of any radio signal they detected was coming from the galaxy versus how much was coming from other sources, including the antenna itself and the atmosphere. This kind of careful calibration is the unglamorous but essential foundation of precision radio astronomy, and Penzias and Wilson were good at it. The problem was the noise. When they pointed the antenna at parts of the sky where there should have been very little radio emission, away from the plane of the Milky Way, toward regions of sky that other astronomers had established were relatively clean, they kept detecting a faint but persistent background hiss, a microwave signal that was about 3 times stronger than their models predicted should be there. It was not a large signal, but it was consistent and real, and it was everywhere they pointed. It did not matter what direction the antenna faced. It did not matter what time of day it was. It did not matter what time of year. Unlike signals from the galaxy or the sun, this signal showed no variation with the Earth's rotation or its orbit. Whatever was producing the hiss was absolutely uniform across the entire sky, and they could not explain it. The methodical process by which they eliminated potential explanations is one of the great examples of scientific carefulness in the 20th century. They checked the electronics. They recalibrated the amplifiers. They calculated the contribution of the antenna itself. Every physical object above absolute zero emits some thermal radiation, and the horn antenna was no exception. They calculated the atmospheric contribution. They looked for interference from New York City 40 miles away. They checked for interference from nuclear tests. There had been atmospheric nuclear tests in the years before the Partial Test Ban Treaty, and these had left detectable traces in the atmosphere. None of these explanations accounted for the signal. It was real. It was uniform. It was everywhere. And then they noticed the pigeons. A pair of pigeons had taken up residence inside the horn antenna and had, as pigeons do, coated the interior with what Penzias and Wilson described in their published paper with magnificent scientific understatement as a white dielectric material, which is a technical way of saying pigeon droppings. The birds were removed. The droppings were cleaned out with considerable effort. The antenna was inspected and found to be in otherwise excellent condition, and the hiss remained. The pigeons, it turned out, had nothing to do with it. By early 1965, after more than a year of trying to explain the signal away, Penzias and Wilson were running out of ideas. And then, through a chain of conversations that is itself a remarkable story of how science actually propagates, through phone calls and preprints and hallway conversations, and the kind of serendipitous connection that happens when the right people are talking to each other at the right moment, they were put in contact with a group of theoretical physicists at Princeton University, about 30 miles away, who had been thinking about exactly the kind of signal that Penzias and Wilson had found. The Princeton group was led by Robert Dicke, one of the most versatile and creative experimental physicists of the 20th century. Dicke had been thinking about the Big Bang and its thermal consequences. He knew, as several physicists had worked out in the years since the late 1940s, when George Gamow and his collaborators had first developed the hot Big Bang theory in quantitative detail, that if the universe had begun in an extremely hot, dense state, and had been expanding and cooling ever since, the thermal radiation left over from that early hot phase should still be present in the universe today. Not concentrated anywhere, not coming from any particular source, but filling all of space uniformly, redshifted by the expansion of the universe from the extraordinarily short wavelengths of the early hot universe to the much longer, cooler wavelengths of microwave radiation today. The temperature of this relic radiation, Dicke and his collaborators had calculated, should be somewhere in the range of a few degrees above absolute zero, cold enough to be in the microwave part of the spectrum, not visible to the eye, but detectable with the right kind of radio receiver. Dicke had actually set his group to building a receiver to search for this radiation. They were almost ready to begin observations, and when Penzias called Dicke to describe the mysterious hiss that had been plaguing his and Wilson's calibration efforts for over a year, Dicke listened and then, in what has become one of the most celebrated moments of scientific recognition in modern history, turned to his colleagues in the room and said, "Boys, we've been scooped." The two papers appeared simultaneously in the Astrophysical Journal in 1965. One, from Penzias and Wilson describing the detection. The other, from Dicke's Princeton group, providing the theoretical interpretation. The pairing was a model of scientific cooperation, though the Nobel Prize that eventually came, in 1978, went only to Penzias and Wilson, to the experimentalists who had actually found the signal, rather than to Dicke and his colleagues who had understood what it meant. This is one of the minor injustices of the Nobel Prize system, which can recognize no more than 3 people for any given discovery, and which in this case left out some of the people whose theoretical work was arguably as important as the detection itself. Dicke, who died in 1997, never received the Nobel for this discovery. The history of science has been kinder to him than the committee was. But what exactly had they found? What is the cosmic microwave background, at a physical level, and why does it exist? To understand this, you have to go back much further than 1965. You have to go back almost 14 billion years, to a time when the universe was not the cold, dark, vast expanse it is today, but something so different from the present universe that describing it requires essentially abandoning every intuition built from ordinary experience. The universe began, or more precisely, the universe as we can observe and describe it began, in an extraordinarily hot, dense state approximately 13.8 billion years ago. The Big Bang. What happened before the Big Bang? Whether there was a before, whether the concept of before even makes sense when applied to the origin of time itself, these are questions that physics cannot currently answer, and we will come back to them. But from the first tiny fraction of a second onward, the universe was expanding and cooling, and the physics of that expansion is well understood, tested, and confirmed by multiple independent lines of evidence. In the very earliest moments, the universe was so hot and dense that even protons and neutrons had not yet formed. The fundamental constituents of matter, quarks and gluons, existed in a free state, a plasma so energetic that the particles that carry the strong nuclear force could not yet confine them into hadrons. Within the first microsecond, as the universe expanded and cooled, quarks and gluons combined into protons and neutrons. Within the first few minutes, protons and neutrons combined into the nuclei of the lightest elements, mostly hydrogen, with about a quarter of the total mass in helium, and trace amounts of lithium and beryllium. This process is called Big Bang nucleosynthesis, and the predictions it makes about the relative abundances of light elements in the universe are among the most precisely confirmed predictions in all of physics. The universe we observe has almost exactly the ratio of hydrogen to helium that the hot Big Bang model predicts, which is one of the most powerful confirmations that the model is correct. But after nucleosynthesis was complete, after those first few minutes, the universe was still far too hot for something crucial to happen. The nuclei existed, but electrons were not yet bound to them. The universe was a plasma, a sea of free electrons, free nuclei, and photons all colliding with each other in a frantic thermal bath. In this state, the universe was opaque. Photons, particles of light, could not travel far before colliding with a free electron and being scattered in a new direction. The universe was filled with light, but it was light trapped in a fog, bouncing around endlessly, unable to travel freely in any direction. This is the same reason the interior of the sun is opaque. It is a plasma, and photons take millions of years to diffuse from the core to the surface through repeated scatterings. The early universe was like the interior of the sun in this respect, but for the entire cosmos. This continued for approximately 380,000 years. The universe expanded, it cooled, and then, at a temperature of roughly 3,000 degrees Kelvin, something happened. The universe reached the temperature at which electrons and protons can combine to form neutral hydrogen atoms and stay combined, stay bound, without being immediately ionized again by a high-energy photon. Physicists call this event recombination, which is slightly misleading since the electrons and protons had never been combined before, but the name has stuck. In a cosmologically brief period, essentially all of the free electrons were swept up into neutral atoms, and the instant that happened, the instant the plasma became neutral gas, the universe became transparent. Photons could suddenly travel freely in any direction without scattering off free electrons, because there were essentially no free electrons left. The fog lifted. For the first time in the universe's history, light could travel, and the light that was released in that moment, the photons that had been trapped in the plasma bouncing around in thermal equilibrium with the matter, that were suddenly set free, began traveling, in every direction, through the expanding universe, for 13.8 billion years, until some of them hit a radio antenna in New Jersey and confused two engineers for more than a year. The surface from which those photons were last scattered, the boundary between the opaque plasma era and the transparent era, is called the surface of last scattering. It is the farthest thing we can ever see with light. Beyond it, in the temporal sense, the universe was opaque. We cannot observe the universe in the first 380,000 years by looking at it with light. Those photons never escaped to tell us about those times. The CMB is literally the oldest light in the observable universe. When we look at the cosmic microwave background, we are looking at the wall of the observable universe in time, the furthest back we can ever peer with electromagnetic radiation. The photons of the CMB that we detect today have been traveling since recombination, 13.8 billion years ago. The universe has expanded enormously since then. The distance scale of the universe has grown by a factor of roughly 1,100 since recombination. And as the universe expanded, the photons of the CMB were stretched along with it. The wavelength of a photon increases as the space it is traveling through expands, and this stretching, this cosmological redshift, has shifted the photons from the red-hot thermal radiation of a 3,000-degree plasma to the much longer wavelengths of microwave radiation today. The CMB we detect is the red-shifted, cooled remnant of the thermal radiation of the recombination era, now corresponding to a temperature of about 2.725 degrees above absolute zero. The universe, since recombination, has cooled by a factor of more than 1,000. What was once a glowing plasma hotter than the surface of many stars is now a nearly imperceptible microwave background that pervades all of space. The uniformity of the CMB is one of its most important properties, and one of the most demanding things it requires of any cosmological model. When astronomers map the CMB across the entire sky, measuring its temperature in every direction, they find that it is extraordinarily uniform. The temperature in one direction is essentially the same as the temperature in the opposite direction, and in every direction in between. The variation is less than 1 part in 100,000. This is a uniformity so extreme that it presents a deep puzzle, one of the central puzzles of modern cosmology, known as the horizon problem. To understand the horizon problem, you have to understand that in an expanding universe, there is a maximum distance over which two regions of space could have ever been in contact, ever been able to exchange light signals and therefore reach thermal equilibrium with each other. This maximum distance is called the causal horizon. Two regions separated by more than their causal horizon could never have interacted, never have exchanged information or energy, never have had any influence on each other whatsoever. They are, in a precise physical sense, causally disconnected. Yet the CMB shows us that regions of the universe that are far more widely separated than their causal horizon, regions that, according to the standard Big Bang model, should never have been able to interact, have temperatures that match to 1 part in 100,000. How did they know to be the same temperature? How did causally disconnected regions of the universe come to thermal equilibrium with each other? In everyday terms, this is like finding that two remote islands, which have never had any contact and lie far beyond any possible communication, have independently developed the same culture, the same language, the same average daily temperature to 1 part in 100,000. It should not be possible. And yet there it is, written across the entire sky. The solution to the horizon problem, the explanation that the modern standard cosmological model relies on, is called inflation. Inflation is the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion, growing by a factor of at least 10 to the 26th power, 10 million trillion times, in an interval of time so brief it is almost impossible to express in ordinary language. The expansion happened faster than light, not violating relativity, because the expansion of space itself is not constrained by the speed of light, only the motion of matter through space. And it took a region that was small enough to have reached thermal equilibrium and stretched it to a size vastly larger than the currently observable universe. If inflation happened, the regions of the CMB that appear causally disconnected were, before inflation, in causal contact. They had time to equilibrate, to reach the same temperature, before inflation stretched them apart. The uniformity of the CMB is, in this picture, a direct consequence of inflation, a memory of the tiny equilibrated patch of pre-inflationary universe that our entire observable cosmos was inflated from. Inflation resolves the horizon problem. It also resolves several other puzzles, the flatness problem, the monopole problem, and makes specific, testable predictions about the properties of the CMB. The CMB is, in this sense, the primary testing ground for the theory of inflation. But we need to go deeper into the CMB because the uniformity is only the beginning of its story. It is the tiny departures from uniformity, the variations at the level of 1 part in 100,000, that contain the richest information. These temperature fluctuations in the CMB are not random. They have a specific pattern, a specific statistical character that reflects the physical processes operating in the early universe. And understanding that pattern has been one of the central projects of cosmology for the past 30 years. The fluctuations in the CMB temperature correspond to fluctuations in the density of the early universe. Regions of the CMB that are slightly hotter correspond to regions of the early universe that were slightly denser. The photons from those regions are slightly more energetic because they formed in a slightly deeper gravitational potential well. And regions that are slightly cooler correspond to regions that were slightly less dense. These tiny density variations, ripples in the density of the cosmic plasma, at the level of 1 part in 100,000, are the seeds of all structure in the universe. Every galaxy, every cluster of galaxies, every filament of the cosmic web began as one of these tiny ripples in the density of the early universe. Gravity amplified them over billions of years. Slightly denser regions pulled in more matter, becoming denser still, eventually collapsing into the first stars and galaxies. The universe went from nearly perfectly uniform to the extraordinarily complex cosmic web we observe today, and the CMB shows us the starting conditions, the initial state from which all of that complexity grew. The pattern of temperature fluctuations in the CMB has a specific structure called the power spectrum, a mathematical decomposition of the fluctuations into components at different angular scales, showing how much fluctuation power exists at each scale. The power spectrum of the CMB has peaks and troughs, what cosmologists call acoustic peaks, that result from sound waves that propagated through the plasma of the early universe before recombination. These were not metaphorical sound waves. They were literal pressure waves, compressions and rarefactions in the plasma, driven by the competition between gravity, which tried to compress the plasma, and radiation pressure, which pushed back. The plasma before recombination was ringing, oscillating at specific frequencies. Like a struck bell or a musical instrument. Different scales oscillated at different phases by the time recombination happened and the oscillations froze in place, and the resulting pattern of frozen oscillations is imprinted in the temperature fluctuations of the CMB as the acoustic peaks. The positions and heights of these acoustic peaks are extraordinarily sensitive to the physical parameters of the universe: the total amount of matter, the total amount of energy, the fraction of matter that is dark matter versus ordinary matter, the fraction of energy that is dark energy, the geometry of space itself. By precisely measuring the power spectrum of the CMB, cosmologists can determine these fundamental parameters of the universe with extraordinary accuracy. This is why the CMB is the primary tool for precision cosmology. It is a dataset of almost unimaginable richness, encoding the values of the universe's most fundamental parameters in the statistical properties of its temperature fluctuations. The spacecraft that have been built to measure the CMB represent some of the most ambitious scientific instruments ever constructed. The first was COBE, the Cosmic Background Explorer, launched by NASA in 1989. COBE was the first satellite specifically designed to study the CMB, and its results were revolutionary. It confirmed that the CMB has a perfect thermal spectrum, the most perfect blackbody radiation spectrum ever measured in nature, consistent with thermal equilibrium at 2.725 Kelvin, to extraordinary precision, a confirmation of the hot Big Bang model so precise and so definitive that it essentially ended any remaining serious scientific debate about whether the Big Bang had actually happened. And COBE detected for the first time the tiny temperature fluctuations in the CMB, the anisotropies that seed structure formation. The COBE map of the CMB was blurry by later standards. Its angular resolution was about 7 degrees, enough to see large-scale features but not the detailed structure of the acoustic peaks. But the detection of anisotropies was a milestone that won the COBE team leaders, John Mather and George Smoot, the Nobel Prize in Physics in 2006. Smoot's description of the COBE results at the 1992 press conference was one of the most memorable moments in the public communication of science. He said, "Looking at the first maps of the CMB anisotropies, if you're religious, it's like looking at God." This was an unusual thing for a scientist to say at a press conference, and Smoot has reflected on it since with a mixture of pride and slight embarrassment. But it captured something genuine about the emotional weight of what they were looking at: the oldest structure in the observable universe, the imprint of conditions a fraction of a second after the Big Bang, the seeds of every galaxy and star and planet and person. The grandiosity of the claim was proportional to the scale of what they had found. After COBE came the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001 and operating until 2010. WMAP was a dramatic improvement in angular resolution and sensitivity over COBE, producing detailed maps of the CMB temperature fluctuations across the entire sky with a resolution of about 1/4 of a degree. The WMAP data enabled the first precise determinations of the cosmological parameters from CMB measurements: the density of ordinary matter, the density of dark matter, the density of dark energy, the geometry of space, the age of the universe. The numbers that came out of WMAP established what became known as the Standard Model of Cosmology, sometimes called lambda CDM, lambda for the cosmological constant, the term representing dark energy in Einstein's equations, and CDM for cold dark matter. The universe is 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. It is 13.8 billion years old. Its spatial geometry is flat, or very nearly so, to the limits of measurement. These numbers, derived from the temperature fluctuations of ancient light, are among the most precisely measured quantities in all of science. Then came Planck, a European Space Agency mission launched in 2009 and operating until 2013. Planck was the definitive first-generation CMB satellite, an instrument of extraordinary sensitivity and resolution that measured the CMB temperature across the entire sky at 9 different frequencies, with angular resolution reaching 7 arc-minutes, and measured for the first time the polarization of the CMB in detail across the whole sky. The Planck data refined the cosmological parameters to unprecedented precision and revealed features in the CMB power spectrum that had never been seen before. The Planck results were published in a series of papers in 2013 and updated versions in 2015 and 2018, and they represent the current gold standard of CMB measurement. But the Planck measurements also revealed something that has become one of the most significant tensions in modern cosmology, a tension that some researchers believe may point to fundamental physics beyond the standard model. When you measure the Hubble constant, the rate at which the universe is currently expanding, using the CMB data and the standard cosmological model to extrapolate from the early universe to today, you get a specific value, about 67 kilometers per second per megaparsec. When you measure the Hubble constant directly, using the local distance ladder, measuring the distances and recession velocities of nearby galaxies and galaxy clusters, you get a higher value, about 73 kilometers per second per megaparsec. These two numbers do not agree. The discrepancy is small in absolute terms but large in statistical terms. It is far too large to be explained by measurement error in either method, and repeated, independent measurements by multiple groups using different techniques have only sharpened the tension rather than resolving it. This discrepancy has become known as the Hubble tension, and it is one of the most actively discussed problems in cosmology. The Hubble tension matters not because of the specific numbers, but because of what their disagreement might imply. If the standard cosmological model is correct, if lambda CDM is the right description of the universe, then the early universe measurement and the late universe measurement should give the same number. They do not. Either one of the measurements is wrong, which is possible but increasingly unlikely as both have been checked and rechecked, or the standard model is missing something. Some new physics, between the early universe and today, that causes the expansion rate to evolve differently than the standard model predicts. Among the possibilities that have been proposed, a new form of dark energy that changes its behavior over time, a new component of radiation in the early universe, a modification of general relativity at cosmological scales, interactions between dark matter particles that have been ignored in the standard model. None of these has been confirmed. The Hubble tension may resolve into a mundane measurement systematic, or it may be pointing at something genuinely new and transformative, a crack in the standard model through which a deeper physics is beginning to show. The CMB is not just a source of temperature fluctuations. It is also polarized, and the polarization carries additional information that is in some ways even richer than the temperature fluctuations themselves. The polarization of the CMB arises from the same scattering processes that produce the temperature anisotropies, and it comes in two types: E-mode polarization, which has a curl-free pattern on the sky, and B-mode polarization, which has a curl-containing pattern. E-modes are produced by density fluctuations and have been measured in detail by WMAP and Planck. B-modes are produced by gravitational waves, ripples in space-time, generated during inflation. Detecting the primordial B-mode polarization signal in the CMB would be direct evidence that inflation happened and would constrain the energy scale at which inflation occurred. It would be, in effect, a photograph of the quantum gravitational processes of the first moments of the universe. This has been described without exaggeration as the holy grail of CMB science. The search for primordial B-modes has been the focus of intense experimental effort. In 2014, a team working with the BICEP 2 telescope at the South Pole announced that they had detected primordial B-modes, a signal consistent with inflation at a specific energy scale. The announcement generated extraordinary excitement. It seemed for a few months like inflation had been confirmed. But subsequent analysis, comparing the BICEP 2 signal with Planck data on the distribution of polarized dust in our own galaxy, showed that the B-mode signal detected by BICEP 2 was consistent with polarized emission from interstellar dust rather than from primordial gravitational waves. The announcement was walked back. The discovery was not confirmed. It was a painful episode for the field, and a cautionary tale about the difficulty of detecting signals that are buried under foreground contamination from the dust of our own galaxy. The search continues. Current and next-generation CMB experiments, including the BICEP array, the Simons Observatory, and ultimately the proposed CMB S4 experiment, are designed with the detection of primordial B-modes as a primary goal. If inflation happened at the energy scale that many theorists consider most natural, the B-mode signal should be detectable by these experiments. If it is not detected, the constraints on inflation will become increasingly severe, ruling out large classes of inflationary models and pushing the field toward either lower energy inflation scenarios or alternatives to the standard inflationary picture. Whether inflation happened, and what kind of inflation happened, is one of the most important open questions in all of physics, and the CMB polarization is currently the best tool we have for answering it. There is another dimension of the CMB story that touches on the deepest and most contested questions in modern physics. Questions about what the uniformity of the CMB, combined with the theory of inflation, implies about the nature of the universe itself. If inflation happened, It stretched a tiny patch of early universe into a region vastly larger than what we can observe. Our observable universe is an infinitesimally small fraction of the total inflated region. But inflation, in most models, does not stop cleanly everywhere at once. Inflation is driven by a quantum field, the inflaton, whose value determines whether inflation is occurring. Quantum mechanics tells us that any field has quantum fluctuations, random variations in its value from point to point. These fluctuations mean that in some regions inflation ends quickly, while in other regions inflation continues for much longer, stretching those regions further. The result, in many inflationary models, is a process called eternal inflation, in which inflation continues forever in some regions even as it ends and produces universes like ours in others. The overall structure is a multiverse, an infinite collection of post-inflationary regions, each potentially with different physical constants, different particle physics, different laws of nature produced by the random quantum fluctuations of the inflaton field. The multiverse is not universally accepted. Many physicists consider it a legitimate theoretical consequence of inflation and take it seriously. Others consider it untestable speculation. If the other universes are genuinely causally disconnected from ours, no experiment can confirm or deny their existence, and a hypothesis that is in principle untestable is in the view of some, not science. This is one of the deepest methodological debates in modern physics, touching on fundamental questions about what science is and what it is for. The CMB is relevant to the multiverse not because it directly confirms the multiverse, it does not and cannot, but because it is the primary evidence for inflation, and inflation is the primary theoretical framework that leads to the multiverse. Every constraint on inflation from the CMB is, indirectly, a constraint on the multiverse hypothesis. There is something almost vertiginous about the chain of inference here. You look at the temperature fluctuations of the cosmic microwave background, you use them to constrain the parameters of inflation, and you find yourself, at the end of a chain of equations and observations and theoretical reasoning, discussing the possibility that our universe is one of infinitely many, that the physical laws we have spent centuries discovering are local accidents rather than universal truths, that the constants of nature, the mass of the electron, the strength of gravity, the energy of the quantum vacuum, are different in different parts of an infinite multiverse, and that we live in the particular part we do not because our values are in any sense fundamental, but because only regions with these values can produce stars and planets and beings capable of asking the question. This argument, the anthropic principle, is either a profound insight about why the universe appears fine-tuned for life, or a way of disguising our ignorance as an explanation, depending on your philosophical disposition. The CMB did not create this debate, but the data it provides is the foundation on which the argument rests. Step back from the philosophy and return to the physics because there is more to tell. One of the things the CMB has taught us that has no parallel in any other data is the nature of dark matter. Dark matter, the invisible, non-luminous substance that makes up about 27% of the universe's total energy content, was inferred long before the CMB era from the dynamics of galaxies and galaxy clusters. Galaxies rotate faster than they should if their only mass were the stars and gas visible in them. Galaxy clusters have more gravitational lensing than their visible matter can account for. Something invisible is providing additional gravitational pull. But what dark matter is, what particle or particles it consists of, how it interacts with ordinary matter beyond gravity, is one of the deepest unsolved problems in physics. The CMB provides independent and precise confirmation of the existence of dark matter and strong constraints on its properties. The specific pattern of acoustic peaks in the CMB power spectrum is sensitive to the ratio of dark matter to ordinary matter, because dark matter and ordinary matter respond differently to the acoustic oscillations before recombination. Dark matter does not interact with photons. It is by definition dark, so it does not participate in the acoustic oscillations. It just sits there, gravitationally, modifying the potential wells that the ordinary matter and photons oscillate in. The detailed shape of the acoustic peaks, their heights, widths, and positions, encodes the ratio of dark matter to ordinary matter in a way that can be precisely extracted from the data. The Planck measurement of this ratio is extraordinarily precise. For every kilogram of ordinary matter in the universe, there are about 5.5 kilograms of dark matter. This number has been cross-checked against completely independent measurements, the dynamics of galaxy clusters, the properties of gravitational lensing, the large-scale distribution of galaxies, and they all agree. Whatever dark matter is, Its abundance is precisely known. Its identity is not. The CMB also tells us something extraordinary about the geometry of space. One of the most fundamental questions in cosmology, one that humans have been asking in various forms for thousands of years, though not always in these terms, is whether space is curved. Is the universe finite or infinite? Does it curve back on itself, the way the surface of a sphere curves back on itself, so that if you travel long enough in one direction you come back where you started? Or is it flat and infinite, extending without boundary in all directions? Or does it have negative curvature, like the surface of a saddle, curving away in both directions and also extending infinitely? General relativity tells us that the geometry of space is determined by the total energy content of the universe. If the total energy density, including ordinary matter, and dark energy, equals a specific critical value, space is flat. If it is higher than the critical value, space has positive curvature. If it is lower, negative curvature. The total energy density is related to the critical density by a parameter called omega, and the departure of omega from 1 is what determines the curvature. The CMB gives us the best measurement of this. The position of the first acoustic peak in the CMB power spectrum is sensitive to the geometry of space, because the geometry determines how far the acoustic oscillations have traveled when we observe them, which affects the angular scale at which the peak appears in the sky. The Planck data tells us that omega is equal to 1.000, plus or minus 0.005. Space is flat, or very nearly so, to the precision of our best measurements. This is one of the most astonishing and demanding results in modern cosmology. The total energy content of the universe is exactly, within measurement precision, the critical value. The universe is flat, and the flatness is itself a consequence of inflation. The exponential expansion of the inflationary era would have stretched out any initial curvature so thoroughly that it is effectively zero in the observable universe today, regardless of the universe's initial geometry. The flatness is a prediction of inflation that has been confirmed by the CMB. Let us take a moment away from the equations and parameters and think about what the CMB feels like to encounter, what it is like to be a physicist or astronomer in the presence of this data. Because there is an emotional dimension to working with the CMB that the technical descriptions inevitably understate. Imagine you are a graduate student or a postdoc, sitting at a computer, looking at a map of the CMB produced by the Planck satellite. The map is color-coded. Blue for regions slightly colder than average, red for regions slightly warmer, and it shows the entire sky, projected into an oval the way the entire surface of the Earth can be projected into an oval map. The color variations are subtle. You are looking at temperature differences of 100,000th of a degree across the sky. And you know, because you have learned the physics, because you understand what the map represents, that every blue region is a place where the universe was slightly less dense 13.8 billion years ago, and every red region is a place where it was slightly more dense. You know that the slight overdensities in red are the places where the first galaxies formed. You know that what you are looking at is the universe before there were any stars, before there were any galaxies, before there was anything recognizable as a cosmic structure. The universe in a state of almost perfect uniformity, with only these tiny ripples to distinguish one region from another. And you know that one of those red regions, one of those slight overdensities, is the seed of the supercluster of galaxies that our solar system lives inside. Somewhere in that map is the wrinkle from which Leniaca grew, from which the Milky Way and Andromeda and all the galaxies of the local group eventually formed. Somewhere in that ancient map of almost uniform light is the specific patch of early universe that eventually, through billions of years of gravitational evolution, produced the sun and the earth and the oceans and the atmosphere and the first life and the first eyes that could look up and wonder where it all came from. You are looking at your own origin, not in a metaphorical sense, but in a literal, physical, traceable sense. The atoms of your body were forged in stars that formed in galaxies that grew from structures seeded by fluctuations that are imprinted in the CMB. Your existence can be traced, link by link, back to those color variations in the Planck map. This is not mysticism, it is physics, and it is one of the most extraordinary things that physics has revealed. The people who built the instruments that measured the CMB, the engineers and scientists who designed the detectors and the satellite systems and the data analysis pipelines, are not always given the credit they deserve in popular accounts, which tend to focus on the theorists and the named principal investigators. But the measurement of the CMB at the level of precision achieved by WMAP and Planck required engineering achievements of extraordinary difficulty. The Planck satellite's detectors had to be cooled to within 1/10 of a degree of absolute zero, colder than any other place in the known universe at the time of its operation, because the detectors needed to be colder than the signal they were measuring. The thermal control systems required to maintain this temperature in the environment of space, with one side of the satellite facing the sun and the other side facing the cold of the cosmos, were a remarkable engineering accomplishment. The data analysis required new mathematical and statistical techniques developed specifically for the CMB, ways of handling incomplete sky coverage, foreground contamination from our own galaxy, and correlated noise between detector channels on a scale that had never been attempted before. The collaboration between hundreds of scientists across dozens of institutions in multiple countries over many years required organizational structures and communication protocols that were in their own way as innovative as the scientific content. John Mather, who led the COBE team and shared the Nobel Prize for its results, spent the years after COBE working on what became the James Webb Space Telescope. A reminder that the community of people who build instruments to look at the early universe and the community of people who build instruments to look at the nearby universe are in the end the same community, connected by curiosity and capability, and the conviction that building better eyes is always worth the effort. The next generation of CMB experiments is being planned and built now. The Simons Observatory, located in the Atacama Desert in Chile at an altitude of nearly 5,200 meters, chosen for the dry, thin air that minimizes atmospheric absorption of microwaves, is currently being assembled and will produce CMB maps of substantially higher sensitivity and resolution than Planck. The CMB S4 project, a proposed collaboration between dozens of universities and national laboratories in the United States and internationally, would place an array of telescopes at both the South Pole and the Atacama and push CMB sensitivity to the level where primordial B modes would either be detected or definitively ruled out at the level expected from most inflationary models. There is also a proposed space mission, the Lightbird satellite, led by Japan's JAXA space agency, specifically designed to measure CMB polarization across the full sky with the sensitivity needed to detect primordial B modes. If funded and launched in the early 2030s, Lightbird would represent the definitive space-based measurement of CMB polarization in this decade. The international effort to squeeze more information from the cosmic microwave background is not slowing. If anything, as the standard model of cosmology has matured and its tensions and open questions have become sharper, the motivation for more precise CMB measurements has grown. There is something it is worth pausing to appreciate about the scientific culture that produced this body of work. The study of the CMB is a multi-generational project. Gamow and his collaborators predicted the existence of relic radiation from the Big Bang in the late 1940s. Dicke and his group worked out the measurable consequences in the early 1960s. Penzias and Wilson found it accidentally in 1965. Kobe confirmed its thermal spectrum and detected its fluctuations in 1992. WMAP mapped it in detail between 2003 and 2010. Planck produced the definitive first-generation map between 2009 and 2013. Ground-based experiments have continued pushing the measurement to smaller angular scales and greater sensitivity, and the next generation of experiments is now being built. The project spans more than 70 years and counting. No individual has worked on all of it. The progress is cumulative, each generation of scientists building on what the previous generation established, making measurements more precise, developing new theoretical frameworks to interpret them, training students who will carry the work into the future. This is what science looks like on its longest timescales. Not a single moment of discovery, but a continuous process of refinement, of squeezing more information from the universe, of developing better questions as the earlier questions are answered. The CMB was a mystery in 1965. It became a confirmation of the Big Bang model by the 1990s. It became a precision measurement tool for cosmological parameters in the 2000s. It is now the frontier where the deepest questions in fundamental physics, inflation, dark matter, dark energy, the multiverse, are being tested. The object of study has not changed. The light is the same light it has always been, traveling through space since 380,000 years after the Big Bang. What has changed is our capacity to hear what it is saying. There is a detail about the CMB that most people, even those who have read about it, never quite grasp in its full strangeness. The CMB is not something that exists in a particular place in the sky. It is not a distant shell at the edge of the observable universe that you are looking at from the inside. In a very real sense, you are inside the CMB. You are surrounded by it. It fills the space you are in right now. The CMB photons are not only coming from a certain direction when you look with a radio telescope, they are passing through the room you are sitting in, through your body, in every direction all the time. There are approximately 410 CMB photons per cubic centimeter of space. About 410 of them in every space the size of a sugar cube, everywhere in the universe, uniformly distributed. In the volume of a typical room, there are on the order of 100 trillion CMB photons at any given moment, all moving at the speed of light in all directions, passing through the walls and the furniture and you, without interacting. They do not interact with ordinary matter enough to be felt or detected without purpose-built instruments. But they are there. They have always been there, for the entire history of the Earth and of life on Earth. Every organism that has ever lived has been bathed in the afterglow of the Big Bang without knowing it. Every moment of every day for 4 billion years of life on this planet, the CMB has been passing through every living thing. We did not know until 1965. We are still learning what it is telling us. It will not always be there, or at least not in the form we can detect it. As the universe continues to expand, the CMB photons will continue to be redshifted to longer and longer wavelengths and lower energies. They will become radio waves, then longer radio waves, then wavelengths so long and energies so low that detecting them becomes technically infeasible. At some point in the future, not soon, not in any time frame relevant to human civilization or even to the existence of the Sun, the CMB will have redshifted to wavelengths so long that even in principle it cannot be distinguished from the noise floor of the expanding universe. It will effectively disappear. The oldest light in the universe, the fossil photon record of the moment matter and radiation decoupled, will be stretched beyond detection. The most important source of information we have about the early universe and the origin of its structure will be gone. This is one of those facts that cosmology occasionally delivers that hits differently from ordinary scientific information, not just intellectually but in some way that is harder to name. We happen to live at a time when the CMB is detectable. If humanity had arisen a trillion years later in a universe far older and far colder, the CMB would be gone, redshifted beyond any technological recovery. Observers in that far future would have no CMB to study, and the evidence it provides for the Big Bang and for inflation and for the seeding of structure, evidence that to us seems definitive and unambiguous, would be unavailable to them. They might construct theories of the early universe, but they would be missing the most powerful observational constraint. They might not be able to determine from the data available to them what the universe was like in its first million years. We live in the right era. The CMB is faint but detectable. The technology to measure it precisely exists or can be built. The theoretical framework to interpret it is in hand, at least in its broad outlines. The window is not closing quickly. We have billions of years before the CMB becomes undetectable, but it is a window, and we are on the inside of it, and the science we can do with it is science that the universe will not permit forever. There is something profound in that. We are not special in the sense of being at the center of the universe. We know we are not. The CMB itself confirms that the universe has no center in the spatial sense. But we are, perhaps, at a cosmologically unusual time, a time when the universe has cooled enough for stars and planets and life and intelligence, but not so old that the evidence of its own origin has been stretched beyond recovery. A time when it is possible to look at the light from 380,000 after the beginning, to read in its temperature fluctuations the seeds of every structure that followed, to reconstruct from its statistical properties the fundamental parameters of reality, and to ask, with some hope of getting an answer, what happened at the very beginning and whether our universe is unique. The people who built Kobe and who worked through the night analyzing its data and who stood at a press conference in 1992 and tried to explain to reporters and cameras what they had found, they were not thinking about any of this necessarily in these large terms. They were thinking about signal-to-noise ratios and calibration procedures and whether the paper was ready to submit and whether the results would hold up under scrutiny. That is what science is made of at the level where it actually happens. The grandeur is real, but it sits on top of years of quiet, careful, technical work that looks nothing like grandeur from the inside. George Smoot, at that 1992 press conference, said it was like looking at God. What he meant, and what the years since have clarified, is that there is a moment when you step back from the calibration and the noise analysis and the map-making and you look at what you have produced, a picture of the universe 380,000 years after the Big Bang, the oldest picture ever taken, the most important picture ever taken, and you understand in a way that goes past the technical details what you are holding, the origin of everything, written in faint temperature variations in the microwave glow that fills all of space. Found by following the physics, building the instruments, cleaning the pigeon droppings out of the antenna, and refusing to stop when the signal did not make sense, Penzias and Wilson never fully understood what they had found in that first moment of recognition. They published the detection paper, and the Princeton theorists published the interpretation paper, and the two appeared side by side, and the cosmological community understood almost immediately that the whole game had changed. But for Penzias and Wilson, who were engineers solving an engineering problem, the emotional impact came more gradually. Wilson, in particular, has said that he took a long time to fully appreciate the cosmological significance of what they had stumbled into, that for months after the discovery was announced, it still felt more like a solved calibration problem than the discovery of the century. The understanding grew with time, the way important things often do. The moment of recognition was a red pen in the hands of no one. It was a paper appearing in a journal in New Jersey and a phone call from one building to another 30 miles away, and two communities of scientists comparing notes on a signal that one of them had found and the other had predicted and neither of them had fully expected. The universe, in the earliest moments it had, produced a flash of light. That light has been traveling ever since through 13.8 billion years of cosmic evolution, through the formation of the first stars and galaxies and clusters and superclusters, through the billions of years of stellar life cycles and the slow construction of heavier elements and the formation of solar systems and the arrival of life on at least one small rocky world. It passed through the atmosphere of that world and into a horn-shaped antenna in New Jersey and registered as a faint, persistent, inexplicable hiss. Two men cleaned up after the pigeons and rechecked their calibrations and called their colleagues, and the universe's autobiography began to be read. We are still reading it. We are still building the instruments to read it better. The oldest light in the universe has been traveling for longer than the Earth has existed, and it still has things to tell us about inflation, about dark energy, about the geometry of space, about whether our universe is unique or one of infinitely many. It passes through you right now, patient and ancient, carrying its message from a time before stars. We are still learning to hear it.